Welcome to qnawire.
So let's first write down the masses of the two collars A and B. The mass of A and the mass of B are identical, so MA is equal to MB, and this is their weight, 2.6 pounds over G, which is 32.2 feet per square second. And so their masses work out to 0.08075. So we'll keep as many decimal points as possible. And that's pound second squared per foot. Now, the first thing we'll do is apply the conservation of angular momentum for collar A. And this means that the angular momentum in state 2, when the cord breaks, should be equal to the angular momentum of the system in state 1, which is the initial state of the system. So HO2 must be equal to HO1. So if you write this in equation form, this is MA R1 V theta 1 is equal to MA R2 and the transverse component of the velocity V theta in state 2. And so we can rearrange this and we can find V theta in state 2. So V theta in state 2 is equal to R1 V theta 1 over R2. And this is equal to R1 squared. We'll replace V theta by R theta dot. So that's R1 squared theta dot 1 over R2. And so this is, we can substitute our values in here, 0.6 squared multiplied by the radial speed, 12 radians per second, over R2, 1.2. And hence we get that the radial component of velocity is 3.6 feet per second. So that's the final radial component of the velocity. Now from here, since we have V theta, we can calculate theta dot. So theta dot 2 is equal to V theta in the second state over RA. And this is equal to 3.6, which we just calculated, over 1.2. So that's 3 radians per second. And we'll use that later on. So now, for part B, let y be the position coordinate of B, and we'll take it as positive upward with a region at O. A constraint of the rod is that R minus y is equal to a constant. And this implies that the second derivative of y with respect to time is simply equal to the second derivative of r with respect to time. So using some kinematics, we can see that the y component of the acceleration of B is obviously y double dot, and this is r double dot. And we also know that the r component, or the radial component of the acceleration of A, is equal to r double dot minus r theta dot squared. So now that we have the accelerations, let's apply them to each color. Let's apply Newton's second law. So for color B, we must have that all the forces in the y direction, when summed, must give the mass of B times its final acceleration, AB. And so this is the tension in the chord T minus the weight of B must equal to the mass of B times y double dot, which we said is the mass of B times r double dot. And we'll call this equation 1. So T minus WB is equal to MB r double dot. Now for color A, we'll apply Newton's second law again. And the sum of all the radial forces must equal to the mass of A times the acceleration of A in its radial component. So the radial forces are due to the tension minus T. So minus T must equal to MA, and the acceleration is R double dot minus R theta dot squared. And this we'll call equation 2. So if we add equation 1 to equation 2, we can eliminate T. So equation 1 plus equation 2 gives us minus the weight of B, WB, is equal to MA plus MB times R double dot d2r dt squared plus MA R d theta dt squared, or theta dot squared. And so what we want to calculate is first the tension and also the acceleration of A relative to the rod. So the first thing to calculate, the acceleration of A relative to our rod, is simply R double dot. So this we can find from rearranging the above equation to be MA R theta dot squared minus the weight of B over MA plus MB. And we can put some values into this. So we get 0.08075 times R, 1.2 times theta dot, which is 3, and that's squared, minus the weight of B, which is 2.6. And this is all over the sum of the masses of A and B, which is 0.08075 plus another 0.08075. Hence we get the acceleration of A relative to the rod to be 10.7 feet per square second, and this acceleration is radially inward. So essentially that's the vector A of point A or color A relative to the rod. The tension T we can calculate as MB into R double dot plus G. So again, we can substitute these values into this. So that's 0.08075 into minus 10.7 for R double dot plus 32.2 feet per square second for G. Hence we get the tension T to be 1.08075 736 pounds.